Hello, this is Miss Nichols, and this is a background video for AP Physics 2 covering some of the topics that are usually covered in AP Physics 1 class. These topics are not heavily emphasized on the AP2 exam, but it is helpful throughout the course of the year to at least have some passing familiarity with them and to be able to use these equations that are on your equation sheet. So the first topic is kinematics. Kin stands for motion, and matics, of course, is the study of. So this is the study of all moving objects. There are 4 essential questions that we'll be talking about in this video. The first is that you should be able to tell what the symbols, definitions, and units of the main kinematics variables are, and also know the math operators that go with them and subscripts. The second is that you should be able to identify which ones of these variables are vectors and which ones are scalars, what those words mean if they're not words you're familiar with, and also what the significance of the sign, positive, negative, or zero, of each variable is. The third is to be able to identify the kinematics equations that are on your equation sheet and decide which ones you should be using. And the fourth is just a factual knowledge. What is the value of acceleration of objects due to Earth's gravitational field? The first kinematics variable that we're going to talk about is known as displacement, sometimes called distance. The symbol of displacement can be either an D, which would be logical, or sometimes it's an X, which stands for sort of displacement in the x-axis, or sometimes it's R, which stands for the radius. So if you're talking about the distance between two sort of round objects, you might see an R represented in the equation, but they all really mean the same thing, which is how far apart two objects are, or how far one object is from a reference point. Displacement is known as a vector variable, which means it has a magnitude, which is another name for size, how big something is, and it also has a direction. That direction in this class is typically either an angle measured in degrees, or it could be a compass bearing like north, south, east, and west. So for example, in the diagram shown, if you took the bottom path to the right, okay, just that first little segment, you would have a displacement of 3 meters to the east from your original starting point. If at your second point you took a path then 4 meters north, right, you would have a displacement of 4 meters from your middle stop, or you would have a net or total displacement of 5 meters at an angle of 53 degrees from your original starting point. So you want to know what 2 points you're measuring from, and then you also have to make sure that you clarify or specify what direction, because you can't just say, I went 4 meters. You could be 4 meters in any direction. So you need to make sure you say, you went 4 meters in a specific direction. And that's what it means to be a vector, and displacement is a vector. The SI, or standard unit for displacement, is usually measured in meters in physics. Of course, we often have really huge things that are in kilometers, and you'll have to convert to meters, or tiny, tiny things, and you'll have to convert back into meters as well for many of our equations. The second physics variable is probably one you're very familiar with from your lives, and that is time. Time is represented by a T, or sometimes delta T. We'll come back to that in a little bit later. The definition is obviously just how long some event will be taking. Time is a scalar variable, so that means it has a size, right? We can say how many seconds, but it doesn't have a direction. Nobody cares about, there's no positive or negative time. It's always positive unless you're in some weird dolly art piece. In any case, the SI unit in physics is the second, and the tool that we use to measure time is typically the stopwatch. The third variable for kinematics is known as velocity. Velocity carries the symbol v, or sometimes v sub x if you're referencing velocity in a specific axis for orientation. Definition of velocity is essentially the same as the direction of speed. It's how fast something is moving, but the difference is that velocity contains this direction piece, which means it's going to be a vector variable. So you have to be able to describe or define velocity both in its magnitude, how many meters it's going every second, and also in the direction that it's going. Positive and negative velocities, if you see a negative velocity pop up, it just means it's going the opposite direction from the positive. So negative doesn't mean slow, it just means left, and positive would mean right. So for example, if that cow went to the right, it would be a positive velocity, and to the left, it would be negative. The SI unit is meters every second, written M over S, And in physics, we would either use a meter stick and stopwatch combination, or there are things called motion sensors that can let you measure velocity directly. The last big kinematics variable is known as acceleration, and this tends to be the trickiest one. Acceleration is a term you've heard before, but you've probably used it wrong. It takes a lot of nuance to really understand what acceleration is. So try to wipe your brain of any idea of what acceleration is, and then we'll replace it with our accurate physics definition. So the symbol for acceleration is a lowercase a, and acceleration is defined as how much the velocity of an object changes every second. So you may have had a sense that velocity meant speeding up or slowing down, and it does, but it's a little bit more specific than that. The challenge in this is that it is a vector variable, but positive velocity or positive acceleration does not mean we're always speeding up, okay? Positive acceleration means the velocity is becoming more positive. So if you start with a positive velocity and you become more positive, well, yeah, your magnitude is going up, you're speeding up. But if you start with a negative velocity and you become more positive, right, that means you're actually slowing down. And there will be a slide in a second that hopefully shows you this in a little bit more graphical way. And of course, the flip side is true with negative acceleration. The SI unit for acceleration is the meter per second every second. This is usually written m per s over s, or m over s times s, or sometimes said meters per second squared. And again, we can measure this with a motion sensor, but it's hard to measure with common tools otherwise. So I'm hoping that this slide can share some common misconceptions and make it a little bit clearer for you. So up here in the top corner, we have an object that has a positive velocity, top left corner. And this is the simple state of a positive velocity with a negative acceleration is going to make you slow down. So that's like running your car through mud. And if you have a positive velocity and a positive acceleration, if they have the same signs, okay, we're going to be speeding up as that velocity gets faster. However, the tricky part happens when we have negative velocity. So we have objects moving in the negative direction, which happens 50% of the time in physics. So it's a lot of scenarios. So if you're moving in the negative velocity direction and you have a positive acceleration, that is actually going to make you slow down as well, because it's going to make your velocity less negative, which is the same as more positive. And the flip side is true as well. If you're moving with a negative velocity and you have a negative acceleration, well, now your velocity is becoming more negative, which is faster and faster and faster. So this, in my mind, is the biggest challenge in understanding acceleration. So you're probably aware that all objects on Earth accelerate when they are dropped, right? You've dropped lots of objects in your life. In terms of physics, we would say that objects with mass are gravitationally attracted to the mass of the Earth. Two objects that have mass like your pencil and the Earth, are going to pull towards each other. Now, it also probably makes sense to you that the more mass an object has, the more it's pulled towards Earth. So I have a pencil and a phone here, and the phone is going to be pulled harder to Earth than the pencil does because it has more mass. And that's obvious. But what is maybe not obvious is that the more mass an object has, the harder it is to accelerate, the more you have to push on it to move, right? If you're outside, you got a little car and a truck, and you want to make them both speed up, you're gonna have to push the big truck a lot harder than you're gonna have to push the little car. So it's interesting, but these effects actually completely cancel each other out. The more mass causes it to be more likely to accelerate because of the gravity, but it causes it to be less likely to accelerate because it's heavier. And so what actually happens is that every single object on the surface of Earth actually has the same acceleration due to gravity. This means that all falling objects will speed up at the same rate. If I take this pen and this iPhone and I drop them, okay, they actually would hit the floor at the same time, despite the fact that they have different masses. There have been some experiments done to prove this. You have to do it inside of a vacuum because air kind of messes with this result. If you got rid of the air on Earth, you would see this for everything, even for things that you might intuitively think are going to fall at really different rates, like a feather and an apple. So this is a picture from a physics lab where they dropped a feather and an apple in a vacuum and took photographs, and you can actually see that they're falling exactly together, which is a pretty cool thing to see. And that acceleration has a value. The value of the acceleration of all objects on Earth is 10, -10. And that comes from a bunch of fundamental constants, which is kind of interesting. But for now, you just need to know in this class that the accelerations of every object on Earth due to gravity is -10 meters per second every second. This is known as little g, aka Earth's gravitational force field strength. And that's a constant that you will be using over the course of the year. So hopefully you remember from ninth grade physics some of your math operators and subscripts, but if not, this should be a really quick refresher. There are 4 math operators that you see in AP equations. Delta means the change in the value of a variable. So some variable will be changing over time, like an object's velocity or its displacement. And you could find that mathematically by taking the final value and subtracting the initial value. That second symbol is known as sigma, and it stands for the sigma or the net or the total of a variable, and that means you're going to add all of the values of that variable together, positive and negative. The little bar is usually on top of a number, or sometimes you see the word AVG as a subscript, or sometimes it doesn't tell you anything, but you just have to know it. Anyway, those mean to take the average value of a variable, so add them all together and divide by 2. Usually in this class, things are changing at a constant rate. You need calculus to deal with things that change at weird rates. And so often this will be the value of a variable right in between the initial and the final value. The last thing is if you see 2 bars bracketing an expression, that means take the absolute value of that expression. Subscripts are the little number or letter next to a variable. If you see a 0 or a little I, that means you want the initial value of that variable. So whatever that value of that variable is when time is starting. If there's no symbol or an F, it usually means that we're talking about the final or the ending value of a variable. And if you see equations that have an X in them, that's usually giving you a hint that that variable is a vector and you need to be considering just the x-axis or any axis you can use, but just a single axis in order to use that equation correctly. And I'll explain this again in the next slide. Okay, so as far as equations that you'll see on your equation sheet that you might need to use or reference in this class, it's kind of a neat thing. You actually only need 2 equations if you really want to go back to the fundamentals of physics, and they are the definition of velocity, which is change in distance over time, and the definition of acceleration, which is a change in velocity over time. However, physicists, I guess, love to make things complicated. So they've taken those equations, they've expanded them into their components, and they've recombined them in different ways. And we'll try this in class once just to see how an equation is derived. But they've taken those 2 very simple equations and they've created 4 much more complicated looking equations out of those 2. And those equations will save you some time. This is 3 of them are shown. The 4th is just that top definition, that velocity definition is distance over time. So the equations that they give you are Vx equals Vx0 plus AXT. And if I was reading that in sort of more colloquial terms, I would say the final velocity of an object is equal to the initial velocity of the object plus the acceleration of that object times time. The next equation, of course, you can read all those equations. So X is going to be the displacement of the final displacement of an object is equal to the initial displacement of the object plus the initial velocity of the object times time plus 1/2 times the acceleration of the object times time squared. And the last equation is the final velocity of an object is equal to the initial velocity of that object squared. Sorry, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration of that object times the final displacement minus the initial displacement. You'll notice all those little X operators in here just tell me that all the vectors in the equation have to be in the same axis. So you can't mix and match motion in this direction with motion in this direction. Your equations won't work. Velocity in this direction is only affected by acceleration in this direction, and will only tell you displacement in this direction. If you try to accelerate an object sideways, it doesn't have any bearing on how far it moves up and down. So you just need to make sure that whatever axis you're in, it doesn't always have to be X, but whatever axis you're in, all of the variables that you use in that equation need to be from the same axis. Okay, so we've reached the end of this slideshow. A good chance to revisit your 3 essential questions, which I put up there again if you want to review them. And I also like to throw a comic up at the end just as a fun way of saying thanks for making it through the video.